Good morning to you all. Continuing our discussion on the nuclear magnetic resonance spectroscopy. The NMR at the present time is considered to be an established technology in a variety of the scientific fields, be it in physics, chemistry, biology, and medicine. We just look back the history of the NMR. It has taken nearly 60 years to reach this interdisciplinary status. And the beauty of this NMR technology is that 3 times Nobel Prize has been awarded for the development of new methods using the nuclear magnetic measurements. In 1952, the Nobel Prize in Physics was awarded for the development of new methods for the nuclear magnetic precision measurements to Professor Edward and Professor Felix. And in 1953, just 1 year after the award of Nobel Prize, the Overhauser observed that the saturation of electrons in metals led to an increase of the nuclear polarization. This is known as, or this effect, it was known later as the nuclear Overhauser effect. And this was the first ever evidence that spins, nuclei or the electrons, could communicate through some spin-spin interactions. That means, in a simple way, the Overhauser effect is about transfer of energy from large electron magnetic moments to protons in the same sample. It was a first evidence that spin could communicate through some spin-spin interactions. In early years, the NMR was a rather insensitive method, and pure liquids were required to detect the NMR spectra. But the sensitivity was significantly improved, or a further gain in sensitivity was provided by the introduction of the FT-NMR. This happened in the year 1966. The ability to excite simultaneously and then unravel all the signals was it was truly a breakthrough or a gateway for the development of numerous pulse sequences. And in the year 1960s, most of the research was carried out on synthetic or natural peptides, and some of the research were also done on paramagnetic proteins such as cytochrome C and myoglobin. Here you can observe that some of the resonances fall outside of the standard range of the chemical shift. So the next refinement of the NMR method was, or the next step was, the introduction of two-dimensional NMR. What happens in two-dimensional NMR or 2D NMR? Here there is an introduction of additional frequency axis, and this led to correlation maps between the spins. And today the NMR is a very unique in the versatility of the multi-dimensional experiments that can be done or implemented. And in 1991, Professor Richard Ernst was awarded Nobel Prize in Chemistry for his contributions to the development of the methodology of high resolution NMR spectroscopy. And in 2002, Professor Kurt Uttrich was awarded Nobel Prize in Chemistry for the development of NMR method to determine the three-dimensional structure of the biological macromolecules in solution. So it has been continuously refined, or the methodology is continuously refined. That is the reason why we see a broad spectrum applications of the nuclear magnetic resonance spectroscopy. You can find it in physics, in chemistry, in biology, and so on and so forth. Right? When we consider about NMR parameters, we know that the NMR spectrum can only be observed when there is a net spin, or when the nuclei possess a net spin. And in this respect, most abundant nucleus in a protein, that is the hydrogen, it is well suited as its most abundant isotope, that is 1H has a spin of 1/2. Now in contrast, the carbon, nitrogen and oxygen, they are not easily visible by NMR, or at least for their most abundant isotopes, that is C12, N14 and O60. Then the question is how to enrich the protein with isotopes. So the answer is isotope labeling, such as C13 and N15. So this is another refinement for the NMR technique. And isotope labeling was supposed to be the expensive strategy in the earlier years, but now the uniform labeling or selective labeling is cost effective. Next we have the chemical shift. So the resolution power of NMR, that is the atomic resolution power of NMR, is intrinsically linked to the occurrence of chemical shift. And as we have studied in NMR spectrum, the magnitude or intensity of the resonance is displayed as, or it is displayed along a single frequency axis in case of one dimensional NMR, or in several axes if it is for multidimensional NMR. So in the spectrum, the magnitude or intensity of the resonance is displayed as single frequency axis or multi-frequency axis or several axes in case of one dimensional and multidimensional NMR respectively. And chemical shift is usually expressed not in hertz but in ppm, that is parts per million, which is relative to a standard that is being used. Using this formula, where V is the signal frequency in hertz and V naught is that of a reference compound. So the chemical shifts in ppm can be compared between the data sets recorded at different field strengths. Right. And several calibration standards are available. One such standard is TMS, that is tetramethylsilane. This is used in organic solvents for the reason that it is, or it has poor solubility in water. So in case of protein analysis, this is replaced by the DSS, that is 2,2-dimethyl 2-silapentane 5-sulfonic acid, especially for protein NMR. We can't use tetramethylsilane, that is TMS, for the reason that it is not soluble or poor soluble in water. So an alternative is DSS for protein NMR. However, to avoid any additional compound that might interfere with the protein, most of the time we use a calibration intermediate. That is the water line, although its position is temperature dependent and pH dependent. So that has to be kept in mind. To avoid any additional interference compound that might interfere with the protein measurement, so a calibration intermediate is used, the water line, even though it is temperature dependent and pH dependent. Measuring the chemical shift or the value of the chemical shift is the most important task of any NMR spectroscopy. And whatever the information that is provided by the chemical shift data, that depends on the availability of the individual resonance assignments. Right. So for example, if the chemical shifts of the compound A change when the compound B is added to the sample, then we know that A and B are interacting. If the resonances of A have been assigned, then these changes can be interpreted at the atomic level. So through such an experiment, if we apply to a protein ligand interaction study, then we can learn which part of the small molecule is interacting and to which part of the macromolecular target the small molecule is bound. Because the chemical shift data depends on the availability of individual resonance assignments. And if compound A interact with compound B when added to the sample, then there is shift of the, or you observe the chemical shifts. So by doing such experiments with respect to protein ligand interactions, you can easily interpret which part of the small molecule or what part of the small molecules are interacting with the macromolecule, or where exactly the small molecule is bound to the macromolecule. Right. So all these informations can be obtained by performing the chemical shift data analysis. Next, we have the scalar coupling, or we refer to as the spin-spin coupling, and it is through bond interactions between the two nuclei with a non-zero spin. Right, and it is an indirect interaction between the two spins that is mediated by the electrons. One spin perturbs the spin of the shared electrons, which in turn will perturb the second spin. So only the isotropic part of the anisotropic interaction is detected in liquid state NMR. Right. If you carefully look at the figure, this figure is about detection of the scalar coupling. We refer this as the J coupling, and nuclear Overhauser effects in one-dimensional NMR spectra. In set A, that is in figure A, it is the reference spectrum which contains 4 signals. They are labeled as 1, 2, 3 and 4. And the 2 signals, that is signal 2 and signal 3, they are singlets. That means only one peak is there. And the other 2 are multiplets, that is signal 1 and signal 4. Now this multiplicity indicates the number of scalar coupled neighbors, but not their assignment. In set B or in figure B, the signal of 4 has been continuously irradiated during the process of recording of the spectrum. That is, we call it as decoupling process. So what is being done is the signal of 4, it has been continuously irradiated during the recording of the spectrum. That is the decoupling process. So the 4 signal is completely bleached out, and the 2 lines of the first signal collapse. That means 1 has been decoupled from 4. That means signal 1 has been decoupled from signal 4. So there is an possible interaction between these 2 signals. So by doing this experiment, it indicates that the spin 1 and 4 are coupled. That is, they are covalent neighbors in the molecule. In set C, in figure C, the signal of 3 has been saturated before the recording of the spectrum. So the 3 signal disappears and the intensity of 1 is altered, but the fine structure remains unchanged. The structure doesn't change. So this experiment evidences a dipolar interaction or a nuclear Overhauser effect between C and A. That means these two nuclei are spatial neighbors, not more than 5 to 7 angstroms. And the absence of the coupling between them indicates that they are separated by more than 5 chemical bonds. Right? So this is a classical example of how the coupling and Overhauser effects can be observed in one-dimensional NMR spectra. So after understanding about the very basics of the NMR and the instrumentation of NMR and some of the parameters of the NMR spectroscopy, what can NMR be used for? So finally, the application side of the NMR. I have listed only few of them, and it is not limited to what the list is. The applications are very broad. Can be used to study gases, solutions and solids, small molecules, macromolecules. Many industries, could be the food industry, the agricultural, pharmaceutical, polymer, healthcare, in small molecule identification and verification, three-dimensional structure elucidation, can be small or even the macromolecules, ligand binding studies, measuring the hydrogen bonds, monitoring the pK values, and probing the molecular motions, and continuously monitoring the enzymatic reactions, and also in quality assurance and control. So these are some of the important applications which has been listed over here, and not limited only to these applications, right? So in concluding remarks, NMR spectroscopy is an effective tool. It is undoubtedly an effective tool for determining the chemical structure. And we have studied that the fundamental idea behind NMR spectroscopy is based on the atom, and an external magnetic field is applied to the nuclear spin, which having a nuclear magnetic moment, and undoubtedly it allows different magnetic potential energies to arise from different spin states. And many investigations have suggested that the electron spin magnetic moment and the proton spin magnetic moment, they are opposite to the electron spin and in the direction of proton spin. So in other words, the spins have nuclear angular momentum and a magnetic moment, for which the magnetogyretic ratio, that is gamma, is the proportionality constant in between them. So with this, I'll stop my discussion over here. We can continue our discussion in the next session with another concept. Thank you very much.